So today what we're going to do is talk about the concept of the mole. And the mole is actually a crucial cornerstone for chemistry. And I don't think it's that complicated as long as you go through like a stepwise process. So today's talk will definitely be crucial to kind of getting what's going to happen for roughly the next month in the class. And so I have this little item here, keep calm and calculate moles. And one of the first, I think, issues where students run into is like, how do we actually, like, what is a mole and why do we need it? So I'm going to step back for a second and just talk about this analogy here. So I have donuts and I have M&Ms. And so a question I always pose in class is, how are donuts and M&Ms sold? And then why? And if you think about it, if you go into a donut shop like Dunkin' Donuts or Krispy Kreme, and you're buying donuts for a class or a group of people, you're going to buy donuts by a dozen. So donuts are normally sold by a dozen, and that's how they're sold. When you go to the store to purchase M&Ms, M&Ms are actually usually sold in bags. So you can buy an individual bag, or if you're buying larger sizes, they're found in pounds. And the reason is why. Well, if you think about it, anything that's small and inexpensive, we package together in larger units to make it easier. If you had to go in the store and handpick out 1,000 M&Ms, like that's just nonsense. It's just going to take forever to accomplish that. But if you go and buy a pound or 2 pounds or 3 pounds, like everyone has a sense on roughly how much M&Ms you're going to get. And atoms are the same. It's just an atom is way smaller than a donut and much more smaller than an M&M. So therefore you need a really large number to make that happen. And the large number that we have is what's called Avogadro's number. So it's the same as a dozen donuts or a pound of M&Ms. And again, atoms are so small, you need a really big number to get easy numbers to work with. So you think about a dozen, there's 12 donuts in a dozen, and a pound of M&Ms, there's like thousands of M&Ms. Because atoms are even smaller than that, you're going to need a really big number to accomplish that. And that large number is 6.022 times 10 to the 23rd, which is Avogadro's number. And Avogadro's number equals 1 mole. So the next thing is, how big is Avogadro's number? So I'm going to pose this question for you. We'll say 1 mole of dollars was created when Earth was created 4.5 billion years ago. And we'll say that I have access to this 1 mole of dollars, and I have decided to donate the money at a rate of $1 million per second. So every second I'm going to give away 1 million. Every 10 seconds I'm going to give away 10 million. Every minute I will donate $60 million. So my question to you guys is go and pause the video and try to answer this question before you move on. When did we run out of money? When did that end? When did I run out? So go ahead and pause it, and when you're ready, restart, and I have the answer on the next slide. Okay. Crazily enough, I still have about 75% of my money left over. So if you think about it, 1 mole of dollars, if you put it in scientific notation, is 1 times 10 to the 6th. So that's 1 mole per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 and a quarter days in 1 year, 4.5 times 10 to the 9th billion years. When you do all that calculation through, you're going to get that I gave away about 1.42 times 10 to the 23rd dollars, and I have 4.6 times 10 to the 23rd dollars left. So Avogadro's number is gigantic. But it makes sense that it would be gigantic because we're talking about atoms. And because they're so small, you have to have this large number to make it work. So what is a mole? What is a mole? So a mole is a number of objects. We covered that. It's 6.022 times 10 to the 23rd. A mole can also be a mass of a substance in grams, either atoms, molecules, or atomic compounds, ionic compounds, which is called molar mass. And then a mole can also be a volume of gas of 22.4 liters at what's called STP. And STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius, and standard temperature is 1 atm. Which is the pressure at sea level. Now, here is the magic of Avogadro's number. So I have a picture here of magnesium. And when I look on the periodic table, magnesium has an atomic mass unit of 24.30 AMUs. So if you look on the periodic table, you have the atomic number and the atomic mass number. And the atomic mass number of magnesium is 24.30. So here's the deal with 1 mole of magnesium. 1 mole of any item is going to be 6.022 times 10 to the 23rd atoms of magnesium. And to get to 1 mole of magnesium, I just need to measure out 24.30 grams, and bam, I have 1 mole of that substance. So any item on the periodic table, if you measure out the atomic mass, that will give you 1 mole of that substance. And you can do this for molecules too. So water. Water is H2O. If you look at the constituents of water, oxygen on the periodic table has an atomic mass unit of 16. Hydrogen has an atomic mass unit of 1.008. There are 2 hydrogens, so 1.008 times 2 is going to be 2.016. When you add that together, you're going to get to appropriate significant digits, 18.02 grams. So how much water molecules are there in 18.2 grams? There's exactly 1 mole in 6.022 times 10 to the 23rd. And given that 1 gram equals 1 milliliter, if we measure out 18 milliliters of water in a graduated cylinder or a beaker, that amount will equal 1 mole, or 6.022 times 10 to the 23rd. This here is just another slide just kind of showing that, the correlation between the molecule, Avogadro's number, and a mole of water. And again, this water sample will be 18 milliliters. So let's talk about sucrose, which is table sugar. What I want you guys to do is calculate how many grams of sugar do you need to get 1 mole. So go ahead and pause the video, look at the masses of carbon, hydrogen, and oxygen, and try to calculate that. And then when you're done, start the video, and I'll have the answer. All right. So the total is going to come to 342.30 grams. If you got that, congratulations. You pretty much understand this concept. So here's how this is going to work. Carbon is 12 carbon are in this. We have the atomic mass is 12.01, so it'll be 144.12 grams. Hydrogen, we have 22 hydrogens. The atomic mass of hydrogen is 1.008, so it's going to be 22.176. And then oxygen, we have 11 times 16 will get us 176 grams. And we add all that together, we're going to have 342.30 grams is going to be our total for that. And that means that that's how much we need grams per mole. So now I have a table for you guys to complete. So I have tin and barium chloride, magnesium hydroxide, and calcium acetate. I want you to calculate the atomic mass. I want you to calculate the number of moles. And I want you to get the number of atoms, molecules, or compounds that this has. Once you fill out this table, go ahead and pause the video to fill out the table, and then start it, and we'll go through the table on the next slide. Okay, here we go. So if you look at the periodic table, tin has an atomic mass unit of 118.71. Barium chloride, we have 1 barium and 2 chlorines. That's going to be 208.23. Magnesium hydroxide will have 1 magnesium and 2 oxygens, and 2 hydrogens will be 58.32. And then for calcium acetate, we have 1 calcium, 4 carbons, 6 hydrogen, and 4 oxygen will be 158.17. Because these are atomic masses for these prospective elements and compounds and molecules, that will all equal 1 mole. And as we talked about, if you have 1 mole of something, you're going to have 6.022 times 10 to the 23rd. Next concept to go over is the mole map. And the mole map is just a simple visual to help you figure out what you need to do to go from point to point. And so gas at STP, and STP is again standard temperature and pressure, 0 degrees Celsius, 1 atm. How to go from gas to moles, how to go from molar mass to moles, and how to go from particles to moles. So moles is the central hub or the exchange rate for bringing these things together. And the best way to organize mole problems is what I like to call doing T-charts. So what's going to happen is we're going to just work on a 1 T-chart first. And so what's going to occur with this is we have a given that I will provide you that will always go in the upper left. What you want will always go in the upper right, and then your unit to cancel will always go down here. You will cross diagonally, and then you'll multiply or divide, and then from that you'll get what you want. So let me go ahead and walk you through this for Gatorade. So the drink Gatorade actually has 52.5 grams of sugar. So the given for Gatorade would be 52.5 grams. So that's going to go up here in the upper left. I need to get 1 mole, so I will put 1 mole of sugar, sucrose, right here. And then the molar mass of sucrose is 342.30 grams. So when I take 52.5 divided by 3, so what will happen is when you have this set up, everything on top you're going to multiply, everything on bottom you're going to divide. So what this chart is telling me, I'm going to take 52.5, I will multiply it by 1, and divide it by 342.3. So 52.5 divided by 342.3 will give us 0.153 moles of sucrose. So using this as a template, this slide here, I want you to convert the following beverages from grams of sugar to moles. So Mountain Dew has 77, Rockstar has 62, and Eggnog has 40. So I'm going to pause the video and give that a shot. The answers will be on the next slides. Okay, so for Mountain Dew, Mountain Dew has 77 grams of sugar. That's our given. That will go in the upper left. What I want is moles, so I'll have 1 mole of sugar, because that's what I want. And then 1 mole of sugar is going to be equal to 342.30 grams. So I'm going to take 77 grams times 1 divided by 342.30. I know I did the calculation correct because the gram unit up here will cancel with the gram unit down here and leave me with moles. So on a calculator, I take 77 divided by 342.30. That's going to give me 0.22 moles of table sugar. Rockstar, given, always upper left, 62 grams. 1 mole of sugar is 342.30. We'll take 62 divided by 342.0. Grams will cancel because they're diagonal. We're left with 0.18 moles of table sugar. And then eggnog, we'll take 40 grams, which is the given. What we want is 1 mole. How to get rid of that? We need molar mass, so it's 342.30 that we calculated earlier. Grams are going to cancel. 0.12 moles will be the answer. So back to our mole map. The examples that we just did were items going from mass to moles. So each of those 3 examples with the beverages. We went from the mass to the moles, and then we set it up in a T-chart, a 1 T-chart to make that happen. So I have some practice problems here. Go and give this one a shot. How many moles are in 500 grams of calcium? Go and set this up. The answer will be on the next slide. So pause the video to accomplish that. All right, so 500 grams of calcium will be our given in the upper left. What we want is 1 mole, and then the molar mass of calcium is 40.08 grams. So we'll take 500 grams divided by 40.08 grams, and that'll get us 12.48 moles will be the answer for that. Next problem, switching it up. We're going the opposite way now. How many grams of calcium sulfate is there in 1.75 moles? So the helpful hint I'll give you is 1.75 moles is the given. So that's going to go in this box. Then you need to cancel moles down here and then put what you want that matches with that moles up here and then work out the problem. So go in and pause the video, try to work that out. When you're done, go and hit play and you'll see it again. Okay, so 1.75 moles of calcium sulfate. The molar mass of calcium sulfate off the periodic table, we have 1 calcium, 1 sulfur, 4 oxygens. When you add up the various atomic masses of all these elements, you're going to get 136.14. We know that moles has to be on bottom because we need to cancel out moles. So it'll be moles here, 1 mole here, and then we're going to go to atomic mass here. We'll take 1.75 times 136.14. That'll get us 238 grams. So back to our mole chart. So we've done 1 mole steps or 1 T steps. So you notice here though, there's ways to go further on the mole map. And so we're actually going to up our game and we're going to go from 1 T to 2 T's. And the basic setup for a 2T chart is mole will need to be in both the second and third column. So usually you'll have a given, you'll have a unit to cancel, mole will be here. Then what your final answer is going to go here, and the mole will then be here to cancel that, and then you'll have your answer. So let's go and see one of these in practice. So on this slide here, given 6.03 times 10 to the 17 compounds of iron 3 chloride, how many grams is this going to be? I'm going to walk you through this entire chart, and this should make sense. So the given is 6.03 times 10 to the 17. I need to get rid of compounds. So I'm going to use Avogadro's number to do that. So 6.022 times 10 to the 23rd to cancel out compounds. That'll give me 1 mole of iron 3 chloride. Then what's going to happen is I need the molar mass because that's what I want. I want grams. The only way to get grams is molar mass. If you add 1 iron and 3 chlorines from the periodic table, that's going to give you 162.20. And then again, the way this works in the calculator, anything on top gets multiplied together. Anything on bottom, you're going to divide. So what's going to happen is there's 2 ways to punch this in. Way number 1, enter 6.03 times 10 to the 17th into your calculator. Then you're going to divide by 6.022 times 10 to the 23rd, and then multiply by 162.20 grams. Or the second way to do this is multiply everything on top and divide by what's on bottom. So 6.03 times 10 to the 17th times 162.20 divided by 6.022 times 10 to the 23rd, and that'll get you 0.000162 grams. So let's go try this one. Given 80 grams of carbon dioxide at STP, how many liters is this? So look at the mole map. look at this chart here and go and pause the video and try to figure this out. And I have the answer on the next slide. Okay, so we're given 80.0 grams. I need to get rid of grams, so I'm going to go to moles. So I need the molar mass of carbon dioxide. So when I add up the masses of carbon and 2 oxygens from the periodic table, I'm going to get 44.01 grams. And then what's going to happen is I'm going to STP. If you look at the mole chart, 1 mole of CO2 at STP is 22.4 liters. So what's going to happen is I want to take 80.0 grams divided by 44.01 grams, multiplied by 22.4. That'll give me 40.7 liters. Or you can take 80.0 times 22.4 divided by 44.01. Your choice if you want to read left to right or multiply everything on top and divide by everything on bottom. Regardless, you should get a final answer of 40.7. Okay, so just to wrap this up, everything kind of stems from the mole math. The mole math will be your best friend. So make sure that you're focused on that. If you are going from moles to something, or from something to moles, you will always use a 1T chart. All 1T charts do is they organize the items, cancel off units so you know that you have the unit you need, and then it tells you if you're going to multiply or divide stuff. So the given always goes in the upper left, what you want always goes in the upper right, and a unit to cancel out the given always goes in the lower right. For 2T charts, what's going to happen is you have the given in the upper left, you have the unit you want to cancel here. What you want will always be in the far upper right, and the unit to cancel is there, and so you should cancel diagonally here and here. You should cancel diagonally here and here, and then the unit you want should stand by itself. This chart here just kind of summarizes what goes on. So to do a 1T, again, it's from or to moles. So it's moles to grams, Avogadro's number, or liters. Or it's from grams, Avogadro's number, and liters to moles. 2T charts will always be grams, Avogadro's numbers, and liters to grams, Avogadro's number, and liters. So it's always good to kind of separate, because you know going in what kind of T-chart you need. It makes it much easier for you to solve these mole problems. Okay, so here is some practice problems. I'm going to go through these. For each one, what I would like you to do is pause the video and give it a shot, and then move on to the next slide, and then you can see the work for that. So mole problem number 1, how many moles are in 500.0 grams of sodium? Sodium's molar mass is 22.99. So when I set that up, I'm going to have 500.0 grams of sodium. 1 mole of sodium is 22.99. So 500 grams is going to cancel. I'm left with moles. It'll be 21.75 moles of sodium. Given 5.03 times 10 to the 19 water molecules, how many grams of this? Water is 18.02 grams per mole. So what's going to happen is I'll put 5.03 times 10 to the 19 molecules up here. 1 mole of water will be over 6.022 times 10 to the 23rd. We'll have 18.02 grams over 1 mole of H2O. So we'll cancel molecules, we'll cancel moles. We'll end up with 0.00151 grams to make that work. So again, to wrap this up, mole map. Wrap this up again. If it's a one, if you're going to or from moles, you're going to use a 1T with this setup. If you're going from an item to a different item, you're going to need 2 T's, and mole will be the item. Just to give you an idea on what you will see as potential quiz questions, I have these 2 questions here. What I'd like you to do is pause the video, try to work out both of these, and then the answers are on the corresponding slides. All right. So for the first problem, given 3.5 moles of dinitrogen dioxide, how many molecules is this? Well, 3.5 moles is of N2O2. We're going to molecules. So molecules is Avogadro's number. So what I want is Avogadro's number is 6.022 times 10 to the 23rd, and that's going to be in molecules. I want to divide that by moles, so it's going to be 3.5 times 6.022 times 10 to the 23rd. That'll give me an answer of 2.1 times 10 to the 24th molecules of N2O2. For problem number 2, we have 90.0 liters of oxygen at STP. How many grams is that? So your given's 90.0 liters. We need to go to moles. We have to get rid of liters, so we're going to put 22.4 down here. That will cancel off liters right here. We'll then put 1 mole of O2, 1 mole of O2 here. Molar mass of O2 is 32.00. So we'll take 90 divided by 22.4. We'll cancel moles here, and you'll have 90.0 divided by 22.4 times 32 will be 129. Or you'll take 90.0 times 32 divided by 22.4 will also give you 129. Now, I know I threw a lot out here on this video. We will go over some of these problems in class the next time I see you guys. So this isn't like the only opportunity that you will have for this. So we'll go through this multiple times in multiple ways. Because again, having a strong foundation on moles will really set you up strong for the next couple units that we're going to do in class. So if you have any questions, as always, make sure to email me, ask me in class, and we will talk about this live at some point. So thanks for your time.